Hello, this is Mr. McGovern. This is the 10th video in the Level 2 Electromagnetism and the last video in Level 2 Electricity. We're going to look at an NCEA problem specifically on electromagnetism. So here we have what looks like a circuit set up where electricity can flow around here, and there's also an external magnetic field, and this rod here can move if there's a force on it. So when the switch closed, the rod moves because there is a force. So which direction does that rod move? Right. So I've got to label the positive of the battery. The long side of the battery is positive, so I know which way current flows. So current flows around clockwise, and up that rod. Electrons, on the other hand, flow the opposite direction. So they're flowing down this way, and that helps me guide which way my hand's pointing. So my left hand is pointing downwards. I then pretend I'm gripping the electrons or gripping the rod there, and I notice that on the right side of the rod, the magnetic field lines from my electrons are going into the page, and on the other side they're coming out of the page, the dots. I'm looking for opposite the external field, so I'm looking for opposite to all those dark crosses, and opposite that is dots, which is on the left side of the rod, so the rod moves to the left. Now I've got to calculate the force. So this is F equals Bill, magnetic field times current times L. I go to write everything down, but I realize I don't have the current, don't have I. So I need to find that first, but the good news is I can use V equals IR, and they've given me a voltage, 12 volts, and they've given me a resistance, 20 ohms. So I can work out that current, then put it into the F equals Bill equation, and work out a force. That was probably a merit question. Alright, now you'll notice that the battery's removed. So it's the same circuit, but there was a battery here, now there's no battery, and I'm doing the pushing of the rod, and it's going to make electricity. So why is a voltage induced in the rod? So I did a whole video on this. There's a long explanation where I say, okay, there's electrons in the rod, and because they're moving, they induce a magnetic field, and then that magnetic field interacts with the external magnetic field and pushes the electrons one way or the other. But I also, at the end of that video, came up with a concise way of writing it. And that way is, if a moving conductor cuts magnetic field lines, so cuts means goes perpendicular to, there are forces on the electrons. This causes a separation of charge, and this is an induced voltage. So I've really got that in my toolkit to use instead of the long sort of 7-step method that I had in the video. Alright, calculate the size and direction. So two things here, flowing through the metal rod when it's moved left at this. So we're now going to do a calculation. So we know there's a formula for the voltage induced. We can work that out. But they haven't asked for the voltage, they've asked for the current. So I've got to go V over R, and that gives me the current. Now I've got to work out the direction. So that was the size. The direction, I am going through this process of what actually happens. So in the wire, or in the rod, there are electrons. Those electrons are moving with the rod. So that's the way my hand points. I grip at the electrons. I've got dots above, crosses below. I'm looking for opposites to the external field. The external field is a whole bunch of crosses. So the opposite has the dots. There's the opposites that's above the electrons. So all the electrons move up. So electrons are moving up through that rod, but current, we know, does the opposite thing. Current is flowing down through the rod, and therefore if you extend it around the whole loop, it's going anti-clockwise. So I think that was an excellent question to get both the direction and the calculation.